Today's lesson is on the concept of the mole and molar mass. The mole is used extensively in chemistry, and so we need to understand what the mole is and how we do use that to determine molar mass. Chemists and scientists deal on two different levels in chemistry. The first level is the macroscopic world, and this is what we can see, weigh, and manipulate in the lab. The microscopic world is where all the chemistry actually happens, where the atoms and the molecules mix together to form new compounds, right? The macroscopic world we can see, the microscopic world we cannot. So in order for us to be able to observe what's happening on the macroscopic world to relate to what's happening on the microscopic world, we need to have some type of conversion factor between the two. And their conversion factor is going to be called the mole. As said in the previous slide, we need a conversion factor to go from the macroscopic world to the microscopic world. And we've called that conversion factor the mole. Now, how the mole works. The mole is an actual SI unit for measuring the amount of a substance. Now, your question could be, well, we already have a way of measuring the amount of material of a substance. Isn't that called mass and or volume? And you would be correct in that. However, the mole is actual measuring amount of substance on a particle size basis. And we'll talk about that, what's the difference is by that in a minute. The mole contains a distinct number of particles, right? It doesn't matter what the particles are, it has the same number of particles in one mole. And that particle number is the Avogadro's number, which is the 6.023 representative particles, which could be atoms, molecules, formula units, whatever, are in one mole. Just as we have 1 dozen equals 12 units, or a baker's dozen has 13 units, or a gross has 12 dozen, a mole will always contain 6.023 times 10 to the 23rd representative particles. Notice in the number there's no mention of any mass or volume here. It's just 6.02 times 10 to the 23rd particles, right? Why is that? Why we measure stuff in mass, but now we were going right to particles. What happened to the mass thing? Well, that's where the conversion comes into play. Now let's think back to the atomic structure unit, right? 1 atom of carbon and 1 atom of aluminum are going to weigh differently because we have more protons and neutrons in the aluminum atom than we do in the carbon atom, right? The carbon atom, 1 carbon atom weighs approximately 12 atomic mass units, whereas 1 aluminum atom weighs approximately 27 atomic mass units. So if you had a box of aluminum atoms, and let's say you had 100 aluminum atoms in a box, and then in another box you put 100 carbon atoms, the box with 100 aluminum atoms will weigh more, right? Because the mass of the aluminum atom is higher, is greater. Even though the box has the same number, the boxes have the same number of atoms, right? When we do chemistry, we don't do chemistry on a mass-to-mass ratio. We do chemistry on a molecule-to-molecule or a atom-to-atom ratio. And that's where we need to convert everything to the mole. The mole basically is the normalization to the number of particles, not the normalization to grams. Okay, in the previous slide, I alluded to why we need to do this conversion. Remember, we measure stuff in grams. Here's our things we measure and weigh out and look at. Grams, liters, that's our macro world. That's where we make our observations. So those are the things we can measure. So we can measure. Can measure, can weigh, can all that stuff. So can measure. But again, as we are into the micro world, where all the action is, it's on the atomic and molecular scale, right? Atoms react with atoms, atoms react with molecules, molecules react with molecules. Heavier atoms will react with lighter atoms, heavier molecules will react with lighter molecules, right? But it's always on a a fixed ratio, 1 to 1, 1 to 2, 2 to 1, right? There's no thing here revolving grams, right? So this is on a fixed ratio, 1 to 2, 2 to 3, whatever, based on the balanced formulas, balanced equations, whereas this can be any number of grams or liters. So we need to have the conversion between here and here to represent that, and that's where the mole fits in. The mole converts the grams into the representative particles. That's the conversion. So it normalizes the masses into number of representative particles. And we go through that using that. So 1 mole is always going to have this number of units. So 1 mole of aluminum will have the same number of units as 1 mole of carbon, even though the masses are different. Okay, so this is what we call the mole triangle, and the mole triangle has 3 corners. The first corner is mass, the second corner is the representative particles, and the third corner is this volume of gas at STP. I am not going to talk anything about that today. Just rest assured that in an ideal gas, 1 mole of ideal gas occupies a fixed volume at all times. At STP, sorry, at standard temperature and pressure. It will every mole, 1 mole of bromine or 1 mole of hydrogen, they all will all occupy 22.4 liters, right? And we'll get into more of that in a little bit later. So just for today, don't worry about this part of the triangle. Concentrate on the mass, representative particles, and mole. Now the concepts that we're going to be learning today are this thing called the molar mass. That's going to be our conversion factor from mass to moles, and I will show you how to calculate that. And then the other thing we've already talked about is our conversion factor from mole to representative particles. We already know that 1 mole has this many representative particles. So if I have 1 mole, this has this many representative particles. And if, let's say, I had a gazillion representative particles, I could figure out how many moles that is by doing the conversion back. So let's figure out. We're going to be able to get by the end of the next couple of videos, we're going to be able to go convert from mass to moles to representative particles, and representative particles to moles to mass. But today we're just going to focus on doing mass to mole and mole to mass. Okay, so let's now get down to the nitty-gritty of how are we going to go from grams into moles, or grams into representative particles. Let's see how we're going to do that. The first thing we need to do is understand how to do this from a grams to moles standpoint. I mentioned to you before that each element's atom will weigh a different amount, right? 1 atom of carbon weighs different than 1 atom of aluminum. 1 atom of aluminum weighs differently than 1 atom of sulfur, etc., etc. But we need to understand how does that relate to the mole, all right? So let's look at it this way. We still don't understand, well, how do we weigh out, when we weigh out like 50 grams of carbon, how do we convert that to moles? What is the conversion factor that we need to go from grams to moles? And it's quite simple when you think about it. Well, once you're told, you'll say, well, aha, that's the aha moment. Remember, each atom has associated with it a specific mass. So 1 atom of carbon, here's my carbon atom, a representative atom of carbon weighs 12.001 atomic mass units, right? Remember that there's no such thing as a 0.001 mass unit. What this is a composite number from all the weighted averages of the naturally occurring isotopes. So there's carbon-13 and carbon-14, as well as carbon-12, which is the most abundant. So when you take the naturally occurring isotopes and you lump them together with the most prevalent isotope, the weighted average is 12.01. So if you took a shovelful of carbon and weighed it, the representative particle on carbon would weigh 12.01 because it's a mixture of carbon 13 and carbon 14 and carbon 12, right? And that's atomic mass units per atom. Now, fortuitously, that we've decided to use this number here as our molar mass. So 1 mole of carbon atoms is going to equal exactly 12.01 grams per mole. 1 mole of carbon atoms is going to equal to 12.01 grams per mole. 1 atom weighs 12.01. One representative atom weighs 12.1 atomic mass units per atom, but when we multiply the collection of atoms by Avogadro's number, we find out now that it's going to weigh 12.01 grams per mole. So there's really no needs to do a special conversion. You can look at your periodic table. This is the atomic mass for each element, and then you mentally make the calculation in your brain that says, okay, if my atomic mass is 12.01 atomic mass units, my molar mass is going to be the same number except in grams per mole. It's that straightforward, right? There's no complicated math. This number here represents two things. The real representation of it is blue. It's the atomic mass, but it's also can be considered now the molar mass, assuming that you put it in grams per mole for the units. So in atomic mass, it's AMUs per atom. In molar mass, it's grams per mole. And that is going to be our conversion factor between the two worlds. We're going to use this new concept called the molar mass. And each element will have a different molar mass because each element has a different atomic mass. Alright, so let's see how now we're going to use our periodic table to determine the molar mass from the atomic mass. Now I gave you a little bit of heads up on the previous slide, but let's look at this real closely again. So now I've given you up here, I've given you the chemical symbol again that we've been from the previous slide. There's my atomic number, here's my element symbol. And now we've said that 1 atom of carbon is going to weigh 12.001 atomic mass units per atom. But also 1 mole of carbon is now going to weigh 12.001 grams per mole. So 1 atom weighs 12.001 AMUs, but 1 mole is going to weigh 12.01 grams per mole. And we now know that 1 mole, or 12 grams of this, is going to be equal to 6.02 times 10 to the 23rd particles of carbon. So 12.01 grams is going to give me 6.02 times 10 to the 23rd particles of carbon. All right. Now let's see how this works with the other elements that we've talked about on the periodic table. Okay, so let's look at a couple more elements here to make sure we understand that. So after I've showed you before that it's all relative to the atomic mass here, let's look at now how another element here, hydrogen. Let's look at hydrogen. Hydrogen has a value of 1.079. I've circled it here. Now, if we convert that to grams, so we make this grams, then that number of grams right here will equal 1 mole, which then will also equal 6.02 times 10 to the 23rd particles. And you can do the same thing over here. You could do the same thing over here with oxygen. Oxygen has 16, roughly 16. And so if you convert that to grams, then that will equal 1 mole of oxygen. Okay, our first activity in this tutorial video is to now for you to determine what the molar mass is of these specific elements. So you're going to use your periodic table and you're going to look up the atomic mass of these elements, and you're mentally going to convert them into grams per mole. And remember, the grams per mole is what we're going to be defining as our molar mass. So I want you to write down the molar mass in grams of all these particular elements here. So here's all these here, look these up, and then write the particular molar mass here. So you should stop the video now, do the exercise. When you are ready to reveal the answers, start the video again and I will give you the answers. So stop the video now. Okay, here are the answers to the problems that you were supposed to do on your own. You should get these numbers, or very, very close to these numbers, using your periodic table. If you're off by, let's say, less than 1/10 of a gram on some of these, you should be fine. If you're off by more than that, you need to go back and make sure that you're using the right number for the element. If you're still struggling with this, you should review the previous video sections, about 10 with the last couple of slides in this, before moving on to the next part of the video. Okay, so we know that chemists don't just mix elements together. We need to understand now, how do we calculate the molar mass of 1 mole of a chemical compound? We know how to do it for an element, so now we're going to do the extension of that and now apply those same principles to calculating the molar mass of a chemical compound. So I've given you the chemical symbol again. Remember, the atomic mass in this particular case, the atomic mass here, is now going to be equal to our molar mass in grams. So the atomic mass in AMUs is going to be equal to our molar mass in grams per mole. So the atomic mass is per atom. Now the molar mass is per grams per mole. So let's look at two simple compounds. Our first compound is water. So here's my compound of water. Everybody knows now that it should be H2O. So 1 mole of water, right? 1 mole of water. Well, let's just break it down this way. First of all, we know that 1 molecule of water has 2 atoms of hydrogen and 1 atom of oxygen. And based on this, atoms to moles, we can do the direct 1-to-1 conversion. So now we have 1 molecule of water. If we convert that to a mole, 1 mole of water has 2 moles of hydrogen and 1 mole of oxygen. We know how to figure out the molar mass of hydrogen, and we know how to figure out the molar mass of oxygen. Since we have a 2 here, because remember the subscript here, we need to multiply the molar mass of hydrogen by 2, because we have 2 of those species in the compound. So that's what we've done over here. We've taken 1 gram per mole of hydrogen. There's 2 of them per mole of water, so we get 2 grams. There's only 1 mole of oxygen per mole of water, and we know that the molar mass of oxygen is 16, so we add that to put that here. And now the molar mass of water is equal to 18.0 grams per mole. We just took the individual elements, multiplied that by the factor that they are in there, or the number of units that they have in the compound, and then we summed up all the individual elements that weighted to get the molar mass of the total compound. And we can apply the same principle down here. We have glucose, which is C6H12O6. We know that 1 atom has 6 atoms of carbon, 12 atoms of hydrogen, and 6 atoms of oxygen. Therefore, 1 mole contains 6 moles of hydrogen, 6 moles of carbon, 12 moles of hydrogen, and 6 moles of oxygen. So it's direct 1-to-1. So you just replace the word atoms with moles. We go to calculate our molar masses, and then the factor we need to multiply each individual mole mass by, because we have 6, 12, and 6 of them. We add them up, and we get 180 grams per mole. So it's really no more complicated than that. You're going to find the molar mass of each individual element, and then you're going to multiply by the number of moles of that element in a mole of compound. And therefore, and then you're going to sum up the total number of grams to get your final molar mass in grams. Okay, our last exercise for this particular concept tutorial is now for you to calculate the molar mass of each one of these compounds, right? Now, we've gone through a couple of examples where we've showed you what the molar, how to treat the 2 and the 2 here and all that. You should know how to do that now. So you should fill out the table here. So again, the same principle applies. You're going to stop the video, write the materials down on a piece of paper, use your periodic table to help you calculate what the total molar mass is for each one of the compounds. You're going to enter that onto your piece of paper, and then when you're ready to come back and get the answers, you're going to start the video again. So stop the video and proceed from there. Okay, so here are the answers to the molar mass for each one of the compounds that's listed on the left-hand side. If you're not getting these numbers, go back and check your math. Go back to make sure you use the correct number of moles of each one of the species in here. For example, in calcium hydroxide, you need to make sure you multiply the 2 times the H and the 2 times the oxygen, because this is in brackets. Same thing here, and go that way. If you're still struggling with these numbers after trying this again, if you struggled the first time, go back and see if you can work it through with the previous couple of slides. If not, you should come and find me so that we get you on the same page, because this concept is going to be built upon for the remainder part of the semester and year.